Log on, tune in, find out. Another good idea from Cambridge.
Okay, so let me first explain the background. So the motivation really comes from studying rigidity of manifolds. Okay, so manifolds are very regular kind of topological object. At every point, there is a neighborhood which is homeomorphic to the Euclidean space. What is rigidity? Rigidity means the following. So roughly speaking, rigidity in general means like if two objects we are studying look roughly the same, they are exactly the same. Okay, so that's what rigidity means in general. But in this context, we can make it very precise. So a compact manifold M is said to be rigid so if whenever another compact manifold N can be like continuously deformed to M. So more precisely, it's homotopy equivalent to M. Then actually N is homomorphic. To M. Okay, so that's what it means. Okay, so at some point it was an open question that is every manifold rigid, but later on examples of compact manifolds were found. I mean, non-rigid manifold was found, and so examples. Examples of non-rigid manifold. The first, kind of example turns out to be relatives of spheres. So it's something. It's essentially the 3rd sphere with some finite group action. Some say actually it can be made to 7. These 7. Okay, so it's I'm not. It's actually the action is very. Actually, the action is very precise. I can give you the action. So you realize S3 as like pair of complex numbers in C2 and so you have like a homomorphism. Okay, so this is a kind of rotation, and if you apply, if you compose this homomorphism 7 times, then it gives you back the identity. So this homomorphism gives you an action of the finite group Z7. Okay, it turns out this is not rigid. Okay, so it's very, very concrete. It's a close relative of the 3rd sphere. Of course, we could ask, the same question about three spheres. That we know is the Boncali conjecture was only resolved recently. So this example was actually surprisingly found to be non-rigid quite a while ago. It's almost close to a century ago.
Another object is shown. No,
yeah, I'm not demonstrating the other object. Actually, the other object, you put a 2 here. Okay, they are homotopy equivalent, but they are not homeomorphic. Okay, so but the concept of rigidity is just about one manifold. But yeah, but the other manifold is also of this type. Okay, all right. So okay, so this is the first kind of non-rigid manifold. So and it's natural to ask the question when a manifold is going to be rigid. So we know that examples like this are kind of difficult to deal with, so we try to stay away from this kind of manifold. So we will focus on a special kind of manifold called so-called asymmetrical. So M is called spherical if the universal cover is contractible. Okay, so for this manifold M, the universal cover is just the three sphere which is not contractible. So an example of an spherical manifold would be M is the torus and the universal cover is Rn. Okay, so this is like a class of manifold which is far away from the spheres. Okay, so the conjecture was that this is called Borel conjecture. So a spherical manifold are rigid. Okay, so this conjecture is still open in general. This conjecture is even quite difficult for Tn. Okay, for example, in dimension 3, this conjecture implies the Boncali conjecture. So although we are trying to stay away from the sphere, and it's no more easy than the sphere. Okay, there is a standard argument trying to you can obtain the Boncali conjecture as a consequence if you know T3.
It wasn't solved in 3 dimensions as a result of the resolution of the Poincare conjecture.
It's not, sorry.
I wonder, but in 3 dimensions, even though we now know the Poincare conjecture, we still don't know Borel in 3 dimensions, right?
In 3 dimension, now actually in 3 dimension, it's essentially solved because of the geometrization. But it's not solved by studying the Borel conjecture. It's solved by different means. Yeah. Okay, so this is the Borel conjecture. Now there is an easy version of the Borel conjecture, what's called stable Borel conjecture. So actually, I have nothing to say about this conjecture, but instead, the stable Borel conjecture. Okay, so the stable. So to formulate the stable Borel conjecture, so I just put stably rigid. If then here I replace so stably, which means by taking a product with some Euclidean space for some. Okay, so the stable Borel conjecture says that just a spherical manifold are stably rigid. Okay, so it's a little bit weaker. It's a weaker conjecture. Okay. All right. So now, actually, one can even consider an even weaker conjecture. Okay. So for that, we have to consider differentiable manifold. For differentiable manifold, we can linearize the manifold. Namely, we can look at its tangent bundle. So tangent bundle gives you some topological invariant, and actually that's an infinitesimal Borel conjecture. Let me just infinitesimal Borel conjecture. So it's an infinitesimal version of both the previous two conjectures. This says that, so now I have to introduce something a little bit technical, but just consider this as a infinitesimal version of the previous two conjectures. So so-called bond, which has some differential invariant, because you take derivatives, so that's how you make things infinitesimal. For this class of manifold. Okay. It turns out for this class of manifold, this infinitesimal version is exactly what's the so-called the Novikov conjecture. Okay. They are equivalent. The Novikov conjecture, of course, can be stated for general manifold, but this is one of the most interesting cases. Okay, so I guess probably the Novikov conjecture is studied more extensively than the previous two conjectures. So there are contributions from many prominent mathematicians. So I will not list all their contributions because the list is too long. And there are also some really great work on the Borel conjecture. Okay, so because since this is a embedding workshop, and I'm going to try to relate the problem to embeddings. Okay, so now why embedding is relevant? If we think about those problems, we are trying to, for a spherical manifold, actually the homotopy information are all contained in the fundamental group, because the high homotopy group of the manifold is the same as the high homotopy group of the universal cover, which is contractible. So all the high homotopy groups are trivial. So all the homotopy information is encoded in the fundamental group. So somehow we need to recognize the homomorphism type from the information about fundamental groups. So we need to somehow recognize the fundamental group, because rigidity, if you think about it, it's a pattern recognition problem. Try to recognize how the manifold looks like. Okay, so we need to impose a condition on the fundamental group. So somehow how you recognize the fundamental group. So that's, I mean, embedding is exactly that kind of condition. Okay, so the kind of embedding we need is really the most flexible kind. So this concept has been mentioned in several talks. Let me just, in case one of you was not in those talks, so to just remind you the concept we need. So if X say is a metric space, or maybe I call it Z. X is a banana space. So a map is called cos Embedding if they exist non-decreasing on the half line such that first okay, for any pair of okay, so roughly the distance of the images in the banana space is controlled by the distance nz. Now, of course, we don't want these functions to be degenerate, so we just need that when the variable is big, this is big. So that's all we need. Okay, so roughly speaking, you are drawing a picture of the metric space Z in the banana space, and the geometry of the banana space roughly reflects the geometry of the original metric space. Okay, so let me just state what kind of result we can prove. So this was I guess last year. So this is actually at the moment this is the best we could do. So this is a result of my colleague. Okay. So if the fundamental group gamma. So this is a finitely generated group. Well, it's actually finitely presented. So we can put a word metric on it. And so as a metric space, this as a metric space is closely embeddable into a banana space. Actually, I have to impose a condition, which I will explain later, but it's with, well, actually, I defined this in the problem section, but I will recall this concept. Then, the Novikov conjecture. Okay. So this is why I was asking the question yesterday that whether C0 has this property. Because every group actually is closely embeddable to C0, into C0. So if one can answer the question for C0, then the general Novikov conjecture follows, which of course sounds like to be too good to be true. But even if you answer that question negatively, it might give us geometric phenomena which might be useful in finding the counterexample. Okay. So let me just say that a special example of this is a Hilbert space.
Remind us what property H is?
Yeah, I will define that. So a special case of is the Hilbert space. I mean, even in the Hilbert space case, maybe I first mentioned that examples of groups costly, embeddable into Hilbert spaces, which satisfy this condition. So hyperbolic groups.
So when you say this, this is generally about groups, or again?
This is general.
Groups. Okay. General.
Yeah, general groups. Hyperbolic groups. So this was done by Sella. So this is was defined by Gromov. It's a very large class of. Okay, then amenable groups. So this is was proved by. Oh, sorry, Becker. Checks. For that. In a way, I mean, if you think about it, it's quite remarkable that amenable group, embed into Hilbert space, because all amenable groups, the geometry are crazy. So you can say something specific about amenable group that's actually quite striking. Okay, so now all linear groups. By linear groups, actually, I'm just looking at a group which is a subgroup of GL and any field. Well, C, let's see. Okay, I'm not assuming it's being discrete, actually. So this is, again, quite striking, because just any group, you just take like finitely many invertible matrices, generate a group. What can you say about its geometry? I mean, it can be crazy. So it's very striking. So this is a result by Higson, Gantner, and Weinberg. The proof is a combination of algebra and geometry. So you can see, even in the Hilbert space case, it's actually it's already very interesting. Okay, all right. So now let me recall what property H means. Well, we call it property H because there is some connection to Hilbert space, but it turns out it's much more flexible. So a Banach space X is said to have property H if there exists an increasing sequence of finite dimensional subspaces, by which I mean linear subspaces of X. Oh, let me just give it a name. And also an increasing sequence of finite dimensional of the Hilbert space let me call it Wn. Okay, such that they exist such that they exist a uniformly continuous function psi from the unit sphere, the union of this subspace, okay, to the union so for which the restriction to each of those subspaces is a homomorphism. From Sn onto, okay. So this sounds it's a little bit technical, but it's very much motivated by geometry of the study of nonlinear geometry of Banach spaces. I was actually, it's the union, yeah.
It's not the sum.
It's the union. But it's an increasing union, yeah. So it's in general it's an infinite dimensional subspace.
Yes, no. So this is a union from
Union of subspaces.
are increasing, I see.
Yeah, it's a union of subspaces. So it's again a subspace, but in general it might be infinite dimensional. Okay, but
It may not be closed.
may not be closed. Yeah, but actually you can extend it because of the uniform continuity. Okay. Okay. So when I opened the book of nonlinear geometrical analysis, I was surprised that this kind of question was actually studied. So an example, just let's look at an example. LP of n. Okay, so what? Take Vn to be, take H to be like L2. Okay, take Wn to be also like B1. Okay, so you just define your psi, C1, to like the sign C1 okay, so and you can check everything is satisfied. Okay, and this map is called the Mazan map. Also, you can check it for, like, if you take X to be CP, the Banach space of Shetland P classes. Okay, so now actually there's some motivation of studying this because studying CP, because one of the questions, so I probably, which there are some general idea of approaching to this question, but it's still no concrete progress has been made. So if you take like a subgroup of the diffeomorphism group of say a manifold. So this is a smooth compact manifold. Actually, it's a conjecture that gamma is causally embeddable into CP for some p. Now, of course, if the answer is positive, what's interesting, it would imply the Novikov conjecture for this kind of groups. Now, this is it's not known. We don't know the Novikov conjecture for this kind of groups. Now, I guess the general idea is the Novikov conjecture, in the end, when I retype, for example, people might find counterexamples. But what we want to prove is that at least for groups from nature, the Novikov conjecture should be true. If it's false, it should be false for a very wild, crazy group we don't even care. So, yes, I'm sorry.
Can you give an example of a space which has not each property?
No, I don't. So this is exactly the question I was asking.
Ah.
So I don't. So I was asking the question, does C0 have this property? And that's essentially a universal question.
Ah.
So maybe I ask this question again. So does C0 have property?
And if C0 has, then any space has.
Essentially, yeah. As far as we are concerned, for this conjecture, if C0 has this property, then we are done. Okay. So that would be really, yeah, wonderful. Yes.
You know an example of a group like that which does not embed in ATP?
The reason is there are some strategy which people have in mind, involving some kind of differential operators and involving commutators. Those commutators are like naturally live here, but not in LP. Okay, so it was because I think the relevant work is, for example, there are some very interesting work by this mathematician. His name is Navas. He did not prove this, but he has in his work there is some ideas one can extricate, and so things were naturally in CP but not in LP. CP is a little bit bigger. It's a non-commutative version of LP. Okay, so if you get bored with my talk, maybe you can try to prove this. Okay, so the proof is very much analysis. I will not get into the details. We use quite some analysis things. Okay, so now.
Guoliang, just
yes.
one more question. So this the ends they don't exhaust X, right? And also.
Oh. Sorry. So they should exhaust. Yeah, I forgot about this. Is a very important. It's dense in X. Otherwise, we can just take. Yeah. Of course, yes. Yeah. Okay, so now I'm going to try to study the stable Borel conjecture, so rigidity. Okay. Now we. So for the rest of the talk, it's going to be joint work, with Eric Gantner and Romain Casala. Okay, so actually, of course, it would be wonderful if we can prove the stable Borel conjecture under the same embeddability condition, but we don't know how. Okay, so instead, we strengthen the condition a little. Okay, so it's what I'm going to. So I'm going to introduce a concept what we call finite geometric complexity, and if you wish, it's a constructive version of embeddability. Okay, so it's going to be more elementary in some sense. But it will imply embeddability, but it works almost equally well for concrete examples, but it's definitely not, it's definitely a stronger condition, okay? Okay, so so for this purpose, I'm going to now to introduce a concept of geometric complexity. So since it's an embedding workshop, you can think of this as a constructive version of embeddability. Although on the surface, it has nothing to do with embeddability. Okay, so let me, I have to introduce some language to formulate this concept of geometric complexity. Okay, so let me first introduce some notations. So I'm going to have, so X alpha, so this is a family of metric spaces, and Y beta, this is another family of metric spaces. Okay. So I'm just going to introduce okay, so now so if I take a positive number, I say that this family of metric spaces can be somehow, with respect to this number R, I can decompose it into Y beta. So what it means is the following. So each X alpha, I'm going to be able to write, so this just means, in terms of notation, it means the following. X alpha, I can write this as the union of two. Okay? And each of them, it will be the disjoint union of J over J. And it's not only disjoint, and it's R disjoint, it's strongly disjoint. So J1, the distance, it's going to be greater than R. If, of course, if J1 is not the same as J2. Okay, so it's kind of strongly. Okay, so this is just a notation. There is no nothing substantial here.
Notation for what?
Oh, good point. So, and Y beta, I just relabel it. Okay, so beta, I just relabel. Okay, so I'm decomposing, I'm chopping it into pieces, and the pieces are Y. So that's, but I'm doing this for family because, as you see, I actually need to deal with just more than one, because even if I start with a metric space, if I do this decomposition, then after a while, I get a family. So that's why I have to deal with a family.
Only two colors.
It's only two colors. Yeah, to make our life simpler. Okay, so now I'm able to define
If Y is bounded size, what you get is asymptotic dimension.
yeah, exactly. So
Only with two colors.
with two colors, but you can do it a number of times. Then you
There's
get,
no restriction on the, except that the X alpha ij come from the family Y, there is no condition on them, just the separation.
yeah, now there's no condition here. Here, because it's just a notation. So now I'm going to get a little bit more serious. So I'm going to formulate this as a game so that we can play some game if we get bored. Decomposition game, okay? So between two players, so player one, player one, I think, is a good guy, okay? Player two is a better guy, okay? So for a metric space X, Okay. Oh, sorry. So I switched the role. Okay. Because prayer 2 is trying to do something good, and prayer 1 is trying to abstract. Okay. So step 1. Prayer 2 says, well, I'm going to give you, a bigger number. Prayer 1 challenges prayer 2. And prayer 2 says that, well, so we are given one metric space. I'm going to decompose this metric space now to like X alpha. Okay, so, and then prayer 2 says, well, I'm going to give you an even bigger number. Okay, so now prayer 2 says, well, I can, now I have a family. I begin with one metric space. I end up with a family. Okay, now I further decompose. Okay, so this process continues. And prayer 2 wins the game if he or she ends up with a uniformly bounded family of metric spaces. Uniformly bounded means that the diameters are uniformly bounded. Okay, so we want to just, and okay. Well, you can try this game on your favorite metric space, whatever it is.
Is this funny?
Hmm?
Is this funny?
It's interesting. Well, if we keep the motivation in our mind. But do you think this is a boring game? Or?
Sort of.
Then think about the Thomason group, okay? You will. Okay, we don't know if you can always win. I mean, if the prayer 2 can always win. Okay, so definition. X is said to have finite geometric complexity if prayer 2 has a winning strategy. I mean, actually, I think Alan is right. I mean, at first glance, it is a kind of boring game. You feel like you can always do that, okay? But just try some examples. Try your favorite examples, and it gets when it gets challenging, it's more interesting, okay? Maybe at least I play one example, okay? Well, it's an easy example, but you see what's going on. X equal to, say, R, okay? Yeah, so I think we all know how to play. So what we do is that, so of course, given an R0, say, step 1. So I'm going to just chop the intervals to like sub-intervals of equal length. I'm just going to choose each one like 10 R0. 10 R0s. Okay, so this is going to, I'm going to label it, well, let me call this Z0, Z1, Z2. So I'm just going to take X0 to be the even numbered ones, and X1 is the odd Okay, you see, the point is that my metric space X, using this language, I'm able to decompose this to the n. Okay, because all those things, the even numbered ones, they are like 10 are 0 apart from each other. So it satisfies this condition. They are apart from each other. Okay, and this family is uniformly bounded because the diameter of each set is 10 R0. Okay, so in one step, I succeeded in decomposing the metric space into uniformly bounded one, just in one step. Okay, now you can think about how to do it for R2. For R2, you need to do it in 2 steps. Okay, you just decompose in one direction and decompose in the other direction. Okay, so
maybe you have to start with player 2, because if it is bounded to begin with, and player 1 chooses R0, which is larger than the diameter, then player 2 cannot.
Oh, no, you cannot stop. In general, no. No, in general, actually, the number of steps required might depend on the choice of the first player. Okay.
But if if R0 is larger than the diameter of X is bounded.
If the diameter of X is bounded, you can always do that.
Say X win the game.
Yeah, then you are done.
That's it. No, you don't. The first step is you choose, player 1 choose R0, which is twice the diameter. Player 2 cannot divide the space into.
No, but then you use one piece and that's it.
Yeah.
All space is one
Yeah,
piece.
but this is not written. Play first to win. This is exactly what I'm saying.
Well, I mean, you can choose the other one to be
You have to
empty.
say that if it is bounded, then player 2 wins.
Yeah.
Okay.
The whole question is interesting just
make it a
for
while instead of
Yeah, if you are bounded, you already, you declare you already win. So we don't do anything. So if it's a bounded metric space, we don't really, we win. So it's the end of the story. Okay. Okay, so so this, and it turns out this concept. So let me just mention to you the kind of examples we have, which have finite geometric complexity. So examples. Because of our motivation, we are always interested in groups. But you can work with this concept for any of your favorite metric space. Examples of groups with finite geometric complexity. Because I mentioned hyperbolic groups, let me mention it again. Okay. And that's easy, that's known. I should mention that there is this concept of finite asymptotic dimension, which Mark already mentioned in his talk. Finite asymptotic dimension actually implies finite geometric complexity. So those groups actually have finite asymptotic dimension. Secondly, I mentioned amenable groups. We are not able to handle all amenable groups. Actually, we can only handle elementary. For example, we don't know the answer for Guoliang group, which are amenable but not elementary amenable. So we don't know if they have finite geometric complexity. That would be a good test case. Okay, so lastly, so all linear groups. So by which again I mean a subgroup of GL like n of any field. So this actually took some serious work. We also had to use the work of Higgs and Gettner Weinberg, but we have to introduce some new ideas as well. This took some hard work to prove this. Okay, so now why is this interesting to us? So and so the reason this is interesting to us is that okay, so this is something we can prove. Okay, so the stable Borel conjecture holds for a spherical manifold whose fundamental groups have finite geometric complexity. Okay, so this was the motivation. So I guess what is interesting for us is that in the literature, the kind of rigidity conjecture are all proved under some hyperbolicity condition. And so our concept, this concept we introduced has much more flexibility. You don't need exactly like hyperbolicity. Okay, so
Is this somehow related in a natural way to topological, or?
not really, because it's much more flexible. It's it's not. It's for example, so like a lot. Well, I guess even among those groups, many of them don't demonstrate hyperbolicity. Okay. Now, for this concept, there are a lot of examples of natural groups we don't know the answer, like the Thomason group. Okay. Maybe so because maybe Alan can think about that, solve it. Yeah. So so we tried a little bit. We were not able to prove it because it has infinite asymptotic dimension. So a lot of groups with finite geometric complexity has infinite asymptotic dimension. So that's exactly why we introduced this concept. And so finite geometric complexity implies cost embeddability because actually this implies the so-called property A. For example, this implies expanders don't have this condition. So right now we have the only kind of metric spaces without this finite complexity expanders, and also the examples of Gonola with Gettner and Specular. So we don't have a lot of examples. If you have examples of metric spaces without this condition, we also would be very interested. So that would maybe tell us how we can improve our condition. Now, another thing I want to mention quickly is that actually this kind of rigidity phenomena also for the Novikov conjecture, especially for the geometric version of the Novikov conjecture. Recently, we were able to prove them even for all the natural expanders we can handle. And also in the algebra world, there is some conjecture called algebraic K-series Novikov conjecture. That's about group algebra over rings. With some special rings, we can prove that it's always true. So in spirit, at least I get a little bit confused where how to what extent rigidity might hold Of course, I think most people are not optimistic that this kind of result will hold in for generality. So, but in any case, the question I raised, if you are able to answer it, would really help us. Well, thank you.
Questions?
Does player 1 really have a role in this, or it's enough if you say that player 2 can hold against some sufficiently rapidly increasing in this game?
Yeah.
Does he have a real role in the game, or is it enough that player 2 can succeed if the sequence grows sufficiently rapidly and that's it?
Oh, actually, we really need to, for it to work for any sequence player 1 might give.
So maybe
But there is no, I mean, you cannot really.
I understand. I'm sorry. I'm sorry. I understand your question. So it's actually we can. Yeah. So that's a good question. So actually, if one can prove it for something like for RK to grow. So I have to think about this sequence, like CK for some C. That would be good enough for us. Okay, so we don't, yeah, that's a good point. But we, so for in the proof, that's all we need. So if we can have this, win this game for this kind of sequence, that would be good enough.
We can send player 1 home. We don't really need him.
yeah, so this,
Yeah, we don't. That's true.
And
But
he's the bad guy. With
yeah, yeah, that's true. Yeah, but that's how. I mean, the examples we have are all, it works for any sequence. So maybe there are some situations this might help. Yeah, this is a good point. Yes, in the proof, that's all we need. Yeah.
Yeah, so there exist finitely generated groups without finite geometric complexity. Is that?
That the only group is the Gromov monster. Yeah, the Gromov's random group, which contains expanders. That's the only example we know. Yeah, so if you find another group, that will be very interesting.
So if we have a finitely presented group,
Yeah.
what do we need to know that it's a fundamental group of an aspherical manifold?
That's an interesting question. That's not resolved. Mark can answer your question.
maybe later, but not now.
I think there's no clean characterization. So, I mean, but there are some. Yeah.
Necessary condition.
Yeah. Well, for example, Mark proved that. For Gromov's crazy group, you can find an aspherical manifold with that fundamental group also.
It is not written yet, but so we cannot say it exists.
Yeah. So.
So let's not.
So okay. So, but you, yeah. Yeah. So. Yeah, we don't have other examples. I mean, it sounds like it's a very naive kind of concept. Yeah, I mean, without the consequence, this may not be that, interesting. But yeah. I don't see, being finite presented would help to check this condition.
Yeah, I only mentioned finitely presented because it's a compact manifold.
Yeah.
So that's why I put that in.
Yeah, but even for finite presented group, we don't know when can be realized as a fundamental group of a spherical manifold. Yeah, we don't know.
One question. If not, let's think this speaker again.